Welcome to Power Electronics Education Electronic Book, Lecture 5, Non-Isolated DC-DC Converters. This lecture is presented by Dr. FIRUZ ZARE. So to find the capacitance value, we can also look at the voltage ripple. So over this period, which is half a switching time, this is the minimum voltage, and at the end of this period the voltage is getting to maximum value. So here we can define the voltage ripple. So that means that V max minus V min equals to 2 delta V, and according to the current through a capacitor we can get the integral over one cycle, and the cycle is defined from T1 to T2. So basically this is the average current, which means this area. We can find this area according to this equation, which is basically the area of this triangle, height side of times of side over 2, and delta V times of 2 equals to V max minus V min. So finally, when we simplify, we get this equation. We know V in, we know duty cycle, we found inductance value, we know switching frequency, and suppose we need to have 5% ripple, then we can find the capacitance value. So in the previous section, we assumed that the current through the inductor is continuous. So in this case, now we are going to consider the discontinuous conduction mode. That means the current through the inductor is not continuous. That means before next switching cycle, so the current through the inductor reached 0. So in this case, we may have different conversion ratio. So this is a boundary case. That means if the inductor current is decreased, then we move to discontinuous conduction mode, or if the inductor current is increased, then we move to continuous conduction mode. So according to this current waveform, we can find the boundary condition when the system can operate either in continuous conduction mode or discontinuous conduction mode. So when the buck converter operates in discontinuous conduction mode, we have 3 different states. So when the switch is on, so in this case we can see that the voltage across the inductor is input voltage minus output voltage. When the switch is off, because the current through the inductor is not 0, then the diode conducts, and then we have this circuit. Because the system operates in discontinuous conduction mode, that means before next switching cycle the current through the inductor is 0, then we have this switching state and this type of circuit diagram. Now we can write the equation again to be able to find the conversion ratio. So again, when the switch is on, the voltage across the inductor is input voltage minus output voltage, and also current through the capacitor is inductor current minus output current. And suppose that the ripple is not significant, then we can rewrite the equation again here. When the switch is off, diode conducts. Again, the voltage across the inductor is minus V out. We can write it here. And the current through the capacitor is inductor current minus output current. Suppose the ripple is not significant, then we can rewrite the equation here. But when the current through the inductor reaches 0, then the voltage across the inductor is 0, and the current through the capacitor is only load current. So we can rewrite the equation here. So when we operate in discontinuous conduction mode, we can see that we have current through the inductor, which is basically equals to load current. So here we can see that the current through the inductor, the average current through the inductor is according to this current waveform, which is basically equals to current through the capacitor plus load current. So that means the AC part can pass through the capacitor and the DC part can pass through the load if the output voltage ripple is not significant. So in order to find the conversion ratio, suppose that the system is lossless, there is not any switching or conduction loss. So the input power equals to output power, that's the average power. So in this case, V in times of I in equals to V out times of I out. So V in input current is basically the current through the inductor just over this cycle, this period, which is basically can be found through this equation. So also we can write the output current, which is V out over R, and we can write the equation here. So in this case we need to find delta I. So basically delta I can be found through this equation. That means again for the first part when the switch is on, we can find the delta I. So basically when we find delta I, we can put it here in this equation and rewrite it here again. So we just need to simplify the equation. And again here, when we write down the equation, we can sort it out based on V in over V out. And suppose this factor is K1. So when we divide the left and right side by V square out, then we can simplify the equation into this equation. So we just need to find this equation. That means when we solve this one, V in over V out equals to 1 plus minus 1 plus 4 K1 over 2. And because this term is greater than 1, so this answer is not correct. And the conversion ratio for this case is V out over V in, which is equals to 2 over this term. So here we can find a boundary condition in which the buck converter can operate in continuous conduction mode or discontinuous conduction mode. So basically the boundary condition is based on this current waveform. So assuming that delta I equals to DC over 2, then this is the boundary condition. That means if DC part is greater than delta I, then the system operates in continuous conduction mode. So because we can find the current through the inductor, that means the current through the DC part equals to output current, and output current is output voltage over resistor. So we can put it here in this equation, and we found delta I before, which is basically V in minus V out over 2L times of DTS. So we just need to simplify the equation, and here we can see that if delta I is less than inductor current, the DC part, then the system operates in continuous conduction mode. We found delta I, which is basically this term, and we found IL, which is basically this term. But because V out equals to duty cycle times of V in, we can put it here, and finally this is the condition. D prime is less than this term, the system operates in continuous conduction mode. Now we can consider boost converter. Basically in boost converter we can increase the voltage level. That means the input voltage is less than output voltage. So we can also control the output voltage magnitude. In this case we can regulate the output voltage, and also boost converter can be used as a PFC, power factor correction. And normally we can use it as a front end for single phase with single phase diode rectifier. So this is a circuit diagram of a boost converter. We have an inductor, we have a diode, we have a capacitor, and we have a switch. and also this is the load. So there are two switching modes. When the switch is off, then we have this sort of circuit, and when the switch is on, we have this sort of circuit. So we can find the voltage across the inductor when the switch is on and off, and then we can find the equation in a steady state. So when the switch is on, here we can see that this is the circuit diagram. So the voltage across the inductor is basically equals to input voltage. So we can write the equation. And here we can see that the current through the capacitor is almost minus load current. Suppose that the ripple is not significant, so we can rewrite the equation as shown here. And when the switch is off, here we can see that the input voltage minus output voltage appears across the inductor. So we can write the equation. And in this case, the current through the capacitor is inductor current minus load current. So we can write it again. Suppose the ripple is not significant, then we can rewrite the equation here. So finally we can draw the output voltage. We can draw the voltage across the inductor. That means when the switch is on, we have input voltage across the inductor, and when the switch is off, we have input voltage minus output voltage across the inductor. Now we can find the equation in a steady state, or we can find the conversion ratio. So as I mentioned before, in order to find the conversion ratio, we can use this equation. That means the average voltage across the inductor should be 0 if the system is in steady state. That means this area should be equal to this area. In this case, the average voltage across the inductor is 0. So here we can see that input voltage times of duty cycle switching time plus this term. When we simplify this equation, finally we can find that the output voltage over input voltage equals to 1 over d prime. So in this case, by changing d prime, we can change the conversion ratio. For example, when d equals to 0, so d prime equals to 1. So in this case, conversion ratio is 1 because d prime equals to 1. And when d approach to 1, then d prime approach to 0, and this term becomes significant, very large. Similar to buck converter, we can find the inductance and capacitance value. So when the switch is on, here we can find the IDT. That means basically this current minus this current is 2 delta I, and here we can find 2 delta I, and we can also find this average voltage. So 2 delta I equals to V in times of dTs over L. So from here we can find the inductance value. So basically, if we know the input current, if we know the input voltage, duty cycle, and switching frequency, and suppose that we're going to keep the ripple 10% of the DC current, or for example 100 milliamps, so in this case we can find the inductance value. So we can also find the capacitance value. That means when the switch is off, the current through the inductor pass through the capacitor and also through the load. We can assume that the current through the capacitor is similar to this one. That means ignoring the ripple when the switch is off. So in this case, we know that when the switch is on, this is the current. When the switch is off, this is the current. Then we can find the average current through the capacitor. So basically here, according to this equation, which is true for any capacitor, we can make the integral over this cycle from 0 up to DTS when the switch is on, then if this ripple is delta VC, that means from this point to that point is 2 delta VC, which is basically here, and because the slope is negative, so we have negative sign here. So it's also same for this current. We know that the load current is V out over R, so that's why in this case the current is negative. So we can also write minus I out, which is basically written here. And because I out equals to V out over R, then we can put in this equation, and finally we can find the ripple in terms of output voltage, duty cycle, resistance value, and also capacitance value plus switching frequency. And because V out equals to V in over D prime, so we can put that one in this equation. So finally we can find the capacitance value, which is basically in terms of these parameters. Now we can consider when the boost converter operates in discontinuous conduction mode. So we have 3 switching states. That means when the switch is on, so this is the circuit diagram, when the switch is off, and when the current through the inductor is getting 0, then this is the circuit diagram. So in this case we can find the voltage across the inductor over one cycle. So we need to find the equation similar to continuous conduction mode. We can find the voltage across the inductor and also current through the capacitor, which is basically same as conduction mode, continuous conduction mode. So when the switch is off, then the current through the inductor passes through the diode and capacitor and resistor. So in this case again the voltage across the inductor is input voltage minus output voltage, which is basically written here, and also current through the capacitor is inductor current minus output current. We can simplify equation again if the ripple is not significant. So now we have these equations. So the last part is when the current through the inductor is getting 0. So in this case the voltage across the inductor is 0, so the current through the capacitor is minus load current, so which is written here. So now we can find the equation for discontinuous conduction mode. That means if the system is lossless, then the average input power should be equal to average output power. That means V in times of I in equals to V out times of I out. So we can find the input current. So input current is basically the average over one cycle, and basically if you look at the inductor current, basically inductor current equals to input current. So we need to find the average over this cycle, because from this point to next switching cycle the current is 0, so we need to find this area. This area we can easily find height times of side divided by 2, so we can find the average. So that means the input current equals to duty cycle plus duty cycle for discontinuous conduction mode times of delta I. When we put this one in the first equation, we get this equation again, and also we can put Vi out, which is basically V out over R, which is given in this equation again. Now we can find delta I. We found delta I before, which is basically V in times of DTS over 2L, and we can put the delta I in this equation. So here we can see that this is the equation which should be simplified, and in this case we need to basically find discontinuous conduction mode, the duty cycle for discontinuous conduction mode, which is given by this term, because from the equation, from the waveform, we found that discontinuous conduction mode when the system is in a steady state is equal to this term. So when we simplify this equation here, for example, we can see that this term is cancelled out, and then we can simplify again, and finally we end up with this equation. So suppose that this term is K2, then we need to find this equation. So when we solve this equation in terms of V out over V in, we have two answers. Because this part is more than 1, so the negative is not the answer, so the positive term is the answer. That means V out over V in conversion ratio equals to this term. So now we can find the boundary condition between discontinuous conduction mode and continuous conduction mode. So let's start with this equation. That means if the ripple is less than DC value of the inductor current, the boost converter operates in continuous conduction mode. So we found delta I before, which is basically equals to V in dTs over 2 times of L, and if we put in this equation, so we end up with this new one. Now we need to find the current through the inductor, which is basically equals to input current. And because input current, as we mentioned, that V in times of I in equals to V out times of I out. So we can find V in terms of V out, I out, and V in, which is here, because V in over D prime is V out, and then we can simplify that one into this equation. So when we multiply the duty cycle and the shift it to the left hand side, then we can simplify the equation. So the point is that this term should be less than 2L over RTS. So we can find the maximum and minimum value of this term. So in this case we define this function, which is d power 3 minus 2 times of d squared plus d. So what's the minimum and maximum value? Here we can find that the maximum value happens when d equals to 1 over 3, or when we put d in this equation, then we can find that this term equals to 4 over 27, and if this is less than 2L over RTS, then the system always operates in continuous conduction mode. Now we can look at the buck boost converter. So in this case the input voltage can be less or more than output voltage, and the point is that the polarity of output voltage is different. That means this is inverting buck boost converter. So this is a circuit diagram. Again, we have a switch, we have an inductor, we have a diode, and we have a capacitor, and this is the load. So when the switch is on, so we charge the inductor, and capacitor is discharged through this resistor, and when the switch is off, then the current through the inductor is pumped into the capacitor and it can charge the capacitor. So now we can find the equation. So basically we have to find the voltage across the inductor. So when the switch is on, the voltage across the inductor is input voltage, and the current through the capacitor is minus load current. Suppose the ripple is not significant, then we can rewrite the equation. When the switch is off, then the voltage across the inductor is basically minus V out, and the current through the capacitor is inductor current minus output current. So basically the voltage across the inductor is given by this equation. That means in a steady state this area should be equal to this area. In this case the average voltage across the inductor is 0, and this is the equation for the capacitor. So basically to find the steady state equation we can simplify. That means finding this area, which is basically V in times of this term plus V out times of this term, and here we can simplify the equation. We can see that d times of V in equals to d prime times of V out. So the conversion ratio here is given by d over 1 minus d, or d over d prime. So here we can see that by changing the duty cycle, we can either increase or decrease the output voltage. So again, we can find the inductance and capacitance value according to the inductor current. We can find the delta I. As we described before, delta I is given by this equation, which is basically we can find the slope of current for the time that the switch is on. And here we can find the inductance value, which is basically is defined by the input voltage, duty cycle, the ripple that we can control, and also the switching frequency. So to find the capacitance value, we can basically find the voltage ripple. Similar to buck or boost converter, we can find the ripple when the switch is on. So in this case, delta VC is given by this equation. We can find I out, which is V out over R. Then we can put in this equation, and finally we can find the capacitance value in terms of input voltage, duty cycle, the maximum ripple for the output voltage, switching frequency, and load impedance. Analyze discontinuous conduction mode for buck boost converter. So again, when the switch is on, we have this circuit. When the switch is off, we have this circuit. And when the current through the inductor reach to 0, then we have this circuit. So basically, similar to continuous conduction mode, we have the equation for inductor voltage and capacitor current, and assuming that simplify the equations. And also when the switch is off, we have same equations. We can simplify the equations, and we can rewrite the inductor voltage and capacitor current. And the last switching state, when the switch is off and when the current through the inductor is getting 0, then the voltage across the inductor is 0, and the current through the capacitor is load current. So here we can basically find the conversion ratio based on this term, input power equals to output power. Again, we need to find the delta I. We found delta I in terms of input current, and we have also delta I in terms of duty cycle and input voltage. So if we put that one in this equation, we can get this equation, and when we simplify that equation, we can find the conversion ratio. Basically, output voltage over input voltage equals to duty cycle times of this term. If we look at the inductor current, here we can see that for this portion of current, this is basically the current through the diode, and the current through the diode has AC and DC part. So DC part is equal to load current, and the AC part pass through the capacitor. So in order to find the boundary condition for continuous conduction mode and discontinuous conduction mode, we need to find output current in terms of input parameters. So we can find the current in terms of inductor current for that period between when the switch is off. So in this case, this is basically the average current through the diode, which is equal to output current. And here we can simplify and finally find the inductor current in terms of load current, which is basically, instead of output current, we can write V out over R. And here we have delta I as well, which is basically equals to this term as we found before. So when we put in this equation, this is the condition for operating in continuous conduction mode. When we simplify the equation, that means finally d prime square should be less than 2L times of R TSW.